Hi everyone, my name is Anvita Bansal and we are back with another lecture based on bit manipulation. So let me just show you the problem statement that we are going to discuss today, and just I'll check if you guys are able to see my screen. Yeah, okay. So I think this works. Moving on. So the problem for today is set kth bit. So let's see what is the problem. Very simple problem. And see, you are given a number n and k, an integer k. You have to set at kth position 1 in your given number. So what does this mean? Let me just take this example. So let's take n is equal to 10. Your n given is what? 10, and your k is 2. So you have to set the second index starting from 0th index from rightmost, that is the least significant bit. When I'm saying you have to change the kth bit in n to 1, that means you are moving from least significant bit. That means your movement is from right to left and starting from index 0, 1, 2. So what bit is present at index 2, that you have to check in n. If it is 0, you set it to 1, right? That's what you have to return. Then your n will be modified. So let's see. Again, we'll be playing around with bits here. We do not need to convert it into its binary form. For your representation, 10 in binary can be written as what? 1 0 1 0. So if you see the indexing, this is 0th index, this is first index, second index and third index, right? So you have to convert k is equal to 2. What is the bit at second index? It's 0. So I want to convert it to 1, and if I convert it to 1, my n will be changed to 1 1 1 0, right? So this is the binary representation when I convert this bit to 1. So finally what you have to return is in the decimal form. So decimal form of this number will be what? 1110 can be written as, not can be, it is 14. How? See, this is 0, then this is 1 into 2 to the power 1 plus 1 into 2 to the power 2 plus 1 into 2 to the power 3. So 8 plus 4 is 12 plus 2 14. That is the answer that you will have to return. So n was given as 10, and to your function you are returning n as 14, because by changing the kth bit to 1, your n got modified, and this is what you are returning. So what can we do? We can simply make use of bitwise operators, or operator and left shift. Now what? Think about it. What can we do? Now, although I have already spilled what we can do, there is nothing much to think of, but still think what kind of operation we can perform on what, so that I can do this thing. I want to set kth bit to 1. If it is already 1, no change is required. If it is not 1, then you need to do some change. Okay, so let's think of what if I'm trying out some possibilities. Let's say your n given is 1 0 1 0. I want to change this bit. So how can I change it? I can do one thing. Let's say I have some number which is 0 1 0 0. That means I have 1 at this position, that is at kth index. Now in order to change it to 1, what can I do? If I do bitwise AND, so you know the modified n will have 1 only if this bit is set to 1, and the modified n will have 0 if this value is 0. So basically I am not making any change to n in that case, right? If it was 1, then it will remain 1. If it is 0, it will remain 0. So I think bitwise AND is not going to help me. That was just for demonstration, that how we come up to what we are doing. So let's see if I use bitwise OR, the OR operation. Okay, if I do bitwise OR of n, this is your n, with some number x, let's say, which has 1 at kth index, then what I'm going to get? See, the final resultant will be, I'm doing bitwise OR. So what is the property of OR? If there is at least one of the bit as 1, then I will set that bit as 1, correct? The resultant will be 1. So this is 1, this is what? Rest of the things will remain same as they were, because when you do bitwise OR with 0, right? So whatever is present here, if it is 1, you will get a 1. If it's 0, you will get a 0. So there will be no change in other bits which are being operated with bitwise OR, right, with X. So the thing that will be changed will be this bit. If this is 0, it will become 1 because of this 1. If it was 1, it will remain 1. There will be no change, and rest of the things will be same, right? I'm sure you all know these things, but that's the number we are getting now. So I think we got our answer. That's what we wanted to do. So this is 0th index, first index, second index. In the original n, the only value that is changed is at kth index, right? Earlier it was 0, now it is 1, and rest of the bits are as it is. So what I want, basically, bitwise OR can be easily done. I want some number x whose binary representation is 0, 1, 0, 0. Or if let's say your k was not 2, k was 3. So 1, 0, 1, 0 is your original number. K is equal to 3 lies at this index, this position. Since it is already 1, I need to see what is present at that index, and I want, let's say now I am choosing x in such a way I have 1 at kth index. So this time my x will be 1,000,000, right? Now you do bitwise OR of x with n. So n and bitwise OR of n with x will be what? This will remain 1. Rest of the things will be as it is, as they are present in n. So there will be no change to n. But if I want a number x such whose binary representation is such that you find a 1 only at kth index and rest are zeros, the rest of the bits are zeros, what can we do? Well, we can definitely choose a number 1. The binary representation of 1 is what? This, as many zeros you want. Now can I do one thing? Left shift your number 1 by k places. Left shift by k. So when I do left shift on 1 by k, what am I doing? I am actually getting rid of bits that are, when I am doing a left shift, I am moving each bit to the left by k positions. So I am removing bits one by one until they are removed. These are the least significant bits, these are the most significant bits. So MSBs are getting removed by k times. So let's say if your k is 2, remove the bits from most significant bit, and if I remove them 2 times, I will be getting rid of starting 2 zeros. So the final number that I'm going to get is 0, 1, and rest will be succeeded with zeros, correct? So that's the number that I'm going to get. So don't you think this ensures that at kth index, this is index 0, this is index 1, this is index 2, this is index 3. If 1, 2 and 3. So if my k was 2, haven't I got a number x whose binary representation contains 1 at exactly second index? So it is as simple as this. You are taking 1, doing a left shift on 1 by k positions. That means if k is 3, you will get 1 at which position? If k was 3, you would have removed 3 zeros and you would have got a number like this, and no matter how many zeros you want, right? Then let's say your original number is 1 0 1 0. Now you do a bitwise OR of this number. So bitwise OR of x and n will be equal to n itself, because kth, if in this case k is 3 and third index 0 1 2 3, third index bit is already 1, so there is no change needed in n, so I am returning n as it is. Okay, so that's the entire solution for this problem, and I hope you are already aware of left shift and right shift in literal terms, as I have already discussed in my previous questions, but iterating it again. Left shift is not just that you mug up this thing that always remove, if I am doing left shift on any number n by k times. So just don't mug it up by thinking that okay, I will remove the first k bits from the starting, that is the most significant bits, and I will shift each bit by k times to the left. So you need to know what is actually happening in terms of decimal number. So if I took 10, 10's binary representation is what? 1010, right? And when I'm doing a left shift on 10 by 2 times, okay, by 2, this actually means this left shift I'm performing on binary only, so obviously its binary representation is being left shifted by 2, then I am getting number 14. But what is actually happening in terms of decimal, actually I'm multiplying this with 2 to the power of k. So 10 into 10 multiplied by 2 to the power of 2. Is there something I missed here? So if I'm doing a left shift on 10, so the answer that I'm going to get is, remove the first 2 bits, then I will get 10 and 00. Okay, so this is what? This is 0, 1, 2, 3, 2 to the power 8. So I think what did I miss here? Just a second. So I have a number 10 whose binary representation is 1010. I did a left shift on it by 2 positions. So I changed this and it got converted to 00. I think that's what it is. And this number is actually what? 0, 1, 2. This is nothing but 8. 2 to the power 3. I'm just thinking what is not going right, because if let's say this is 2, so how do you represent it? I do a left shift on it by 2 times. 2 to the power 2, 4, right? So that number is actually getting, ideally it should be multiplied by, what is not going right? 0010. Let's say this is your number. Okay, so I was doing that wrong. Fine. Coming back to the logic, what I was trying to explain. Yeah. So in terms of decimals, what is happening is you are multiplying that number by 2 to the power of k. If n is the decimal form of the number and I am doing a left shift on n by k times, so actually what is happening is n is getting multiplied by 2 to the power of k. So this is what is happening. If k is 2, so n is multiplied by 2 to the power of 2, that is 4. So let's say your n is 2, right? So when you multiply it by 2 to the power 2, that becomes 4. So the answer is 8. So let's verify in terms of binary. So 2 can be represented as 0010, right? When you do a left shift on this binary by 2 times, so you remove the most significant bits, shift each bit one by one. So when you do, and you are moving them here, so you get 0, 1, 0, 0, 0, right? You shift it here, and each of them gets shifted by left, okay, to left by k times. So this is the number you are getting. So what is this? What is the decimal representation of this binary number? That is 2 to the power 3, right? Because 0, 1, 2, 3. So 2 to the power 3 into 1, that is 8. So we verified both the answers are same. So that's what is happening. And vice versa for right shift. In right shift, what is happening? The number n which is being right shifted by k times, right? So that number actually in terms of decimal, n is getting divided by 2 to the power of k, right? That's all. So let's quickly code it. Let me check what is the status. Yeah, let me see what is your doubt, guys. Just a sec. So okay, Sai Harsha, can you elaborate what you want to understand? I'll take up your question. Meanwhile, I'll just write, that's just one line of code, nothing else. You will just have to return what we discussed here. So your answer is return 1. You are left shifting 1 by k times and doing bitwise OR with the given number n, and that's what you are returning. Okay. Let me check by that time if you have any doubts. Let's submit it. So that's all for today then, guys. If you do not have any doubts, we will wrap it up. Okay. Fine then. That was all for today. See you all in the next lecture. Bye bye.